Hey everybody. So I thought I'd do a quick stream here since I ended the the lecture series on typological neuroscience because I want to keep that info secret for now. I figured I'd do something a little fun, something I've been messing around with that I think is often. I mean, I had a little bit of exposure to this as part of my college curriculum, not a whole lot though, and I think it's a really interesting kind of tool to have for certain kinds of problems. So what we're going to be talking about today is variational calculus a little bit, but for the kind of the focus of this one is going to be the principle of least action. That's what we're going to spend most of our time on. But basically, variational calculus is the tool used when applying the principle of least action. Okay, so what is the principle of least action? Right, so I guess I can start by giving you something boring by just a definition. We define action, okay, using this letter S. All right, and we need something more chill than this. Give me a second. I thought Danganronpa would be good, but I think what we're gonna do instead is what do I want to do here? I mean, I kind of want to go to maybe this one. There we go. All right, this is appropriate. Anyway, action is defined as this S, and it's equal to this integral here. So from t1 to t2 of something called the Lagrangian, which we denote with the letter L, and we integrate over the entire of the time domain of the path that the kind of particle or whatever is of everything's taking, right? So we kind of treat time here as kind of the ultimate the kind of dimension here. I suppose, I mean, mathematically you can think of it in terms of spatial coordinates too, but generally in mechanics you kind of treat time as kind of this sequence of things happening as opposed to kind of a spatial dimension, and that's kind of what we're going to be doing today. So I'm going to go ahead and give you kind of a basic example that I kind of developed that I think is a good way to go over this. So let's say that we have kind of a 1D universe here, 1D plus time, right? We got this line, right? We'll call it the x-axis, and this is the positive direction, okay? And let's say we have a particle right here. This is its starting position. All right. X of t1, and then it kind of moves along, right, with a constant velocity. All right, it's constant velocity, which actually makes it very, very easy, but we're going to treat it as a non-constant parameter just to kind of prove a point here at the end. So then it kind of goes to point B here, right? And now it's at x of, instead of t2, we're going to call it big T. And the reason that we're going to do that is so that we can kind of use it as a variable in our equations of motion, right? We want to be able to pick any value of t and figure out what this particle is doing at any point in time, right? And let's think about what's going to happen here. If it's moving at a constant velocity, right, it's just going to kind of move along. You probably already know what this equation looks like even. It's something like x of t is equal to velocity times time, right, plus x of t1, right, which is our initial position. That's probably what you're used to. In fact, that is right. But the point of this here is not to actually say that you need to use the principle of least action to derive something like this. The point is that you can, and it gives you an ability to think about more complicated problems if you want to. And additionally, right, we know that, this is obviously a 1D space, but what if it was a 2D space, right? There's a lot of different ways we can get to point B, right? We could kind of go over here and then come over here, right? We could kind of wiggle around and we could, right? But that's not really what's going to happen. That's kind of a complicated path, isn't it, right? So most likely it's probably just going to go from point A to point B without really much trouble. Or in what we would call the least amount of action, right? So action conceptually, it's kind of, it's not really work. I guess you could think of it as work integrated over time, maybe, right? Because L does have units of energy, right? So we're basically saying how much energy, right, is does the system have, and then kind of integrating that over time. So basically what the principle of least action says is that our system is going to follow the path that minimizes the action, right? So we can put action S on the let's say this is our velocity function or something, or really any function. It can be our position function, it can be the point is that instead of it being a variable, it's actually our axis is kind of a function, which is a weird way to think about it, but I think it'll make more sense maybe once I explain more of it. So maybe we might have a shape like this. If we pick certain functions, right, we'll have an action like this. We might have an action here, but what we want is the point that minimizes the action, right? If you've ever taken calculus, if we were to cross this out and say this is the time axis or something, right, we would just say, okay, well, let's figure out what S is, take its time derivative, and set that equal to 0, and then check to make sure that the second derivative is greater than 0. Right? That's a pretty straightforward. What we're basically doing is the same thing, except we're applying it not to a time variable, but an actual function. All right. So the next step I think I'm going to do is define the Lagrangian. So I threw this L in there earlier. What even is that? Well, it's pretty simple, actually. It's basically just, oh my god, that is kind of loud. At least it's loud on my end. Hopefully, I hope it probably won't be that big of a deal. But basically, the Lagrangian is the kinetic energy, which we denote as a T, minus the potential energy, which we denote with a V. All right. So in this system, right, we have a particle, some constant velocity, or actually we're gonna treat it as non-constant, but we know it's supposed to be constant, and so we're gonna use that as kind of a check to make sure we're kind of on the right track later on. So let's set that equal to 1/2 mv squared. So, by the way, I probably should have mentioned this at the beginning. This assumes you already have some kind of calculus knowledge and some kind of basic physics knowledge. You should at least be able to integrate and differentiate velocity, position, solve some differential equations. A little bit of that. I don't think it's probably more complicated than I'm making it out to be. But if you ever feel lost or you just have no idea what's going on, you don't need to watch. You don't need to watch it. I'm not gonna tell you that. No, just wait, it'll make sense. No, this is designed clearly. This is honestly probably more of a third-year undergrad or even a graduate school concept, honestly. Although in grad school they would probably give you these annoying formal definitions on paper that don't even make any sense, don't even make any intuitive sense, and are a nightmare to read. And so I'm trying to make it more intuitive so that more people can understand these kind of things. So anyway, we're going to subtract the potential energy, except that actually we don't have any potential energy. There's no gravity, there's no springs, no nothing, so we don't even have to worry about that, right? So what I'll go ahead and do is then, okay, what I'm going to do is plug that into my action integral, I guess. So from t1 to t, 1/2 m v squared d guess we'll use a little t here, just to keep it that the kind of the our final t, which is like the t we select and kind of the t we're integrating over. Okay, so now we have this integral. So we're supposed to minimize this action quantity, right? How do we do that? Okay, how do we minimize action? Right? Well, kind of interesting because I guess we could try differentiating it, which in this case might actually work because we could just treat our velocity as constant, and then we'd kind of just be able to, and maybe I can even do that right now. So we'd have like 1/2 mv squared out here, and then we'd end up with something like t minus t1, right? And then I guess basically what we would have to do is just pick a variable to what are we trying to minimize here. I guess one problem with this though is that if you look at it, pretty much no matter what, we could just set like anything equal to 0, except that doesn't really make any sense. And this is why we end up having to kind of use differential equations to do this kind of thing. So what I'll talk about now is taking a variation, which is what we're going to have to do to minimize this. It's analogous to a derivative, but instead of for a variable, it's minimizing a function with respect to another function, right? And if a function is a function of another function, that's called a functional, right? Taking a variation. So let's say we have some function, right? Some function f, right? And it's a function of g, which is a function of t, right? If we wanted to take the variation of this, we use this I forget what the operator is called, but it looks like this. So we're going to take the variation of f here. And so what we do is basically the chain rule, right? The chain rules, maybe there's some formal proofs that I'm missing here, but essentially it works the same way. We take the derivative of this, wait a minute, is that right? I'm thinking. Yeah, we take the derivative of this outside, a partial derivative actually. So the partial derivative of f with respect to, in this case, this is our function we're trying to look at here. So partial derivative of f with respect to g. And then what we do is we basically take times the variation of g, okay? If we can put t there if we want to. And really all this is saying is this is basically just y equals mx plus b. So, y equals mx, or actually it's more like y equals mx, kind of like that, where we've got our, basically what we're saying is that as we vary g, the function g, right, we multiply by how f changes as g changes, and then we get how f varies, right? So that's kind of intuitively how that works. So now what we're going to do is we're going to apply this principle. And one note to make here that it's not entirely obvious if you're trying to learn this stuff on your own, but you can move variations inside integrals. You can move variations inside integrals, right? So what this basically means is if I have some basically big integral of t or whatever, and it's equal to something like this, and I want to take a variation, I can do the variation of f of t, and that would be equal to this variation, right? Because we're doing the same operator on the same quantity here. So what I can do here is say, okay, I'll do the variation of variation of g of t. I just made a q there, my bad. If you look up the general stuff for this, they usually use q's, but I kind of like the f and g. That's just kind of what I grew up with. So variation of g of t, and then if we wanted to, we could go even deeper and say, okay, well, how about the partial derivative of g with respect to t times the variation of t, right? We could do that too. But it's kind of up to us, you know, to use our kind of insight to be like, okay, when do we stop? Where can I, you know, but let's go ahead and apply this to our example case here. So if you recall, we had something like t1 to t of 1/2 mv, and we'll go ahead and v of t here to remind ourselves that we're treating this as a function, not a constant here, times dt. So we're going to go ahead and take the variation, and because we're minimizing it, just like we want to set the derivative equal to 0, we're going to set the variation of s equal to 0, right? Because once we're on that bottom point, the action should not vary at all for our system. It should just stay constant, so that should be equal to 0. Okay, so here we go. Variation of s. I'm going to go ahead and move it inside the integral here. Another thing about variations, you can factor out constants too. That's another thing. So in this case, 1/2 m is a constant. Our mass isn't changing in our... We could actually make a system where mass like magically like goes up and down or something if we wanted to, but you know, maybe that you can do that yourself. Try to piece that together. Most likely it won't work out, because anytime you try to do something after one example, it never works out. But anyway, let's go ahead and do this. 1/2. Actually, I'm gonna go jump a few steps ahead here. So we're gonna end up taking a partial derivative of this quantity, which means that, you know, the 2 is gonna go down. So we end up with mass times v of t. Then times the partial derivative of v of t with respect to t, the variation of... Wait a minute. Uh-oh. I'm thinking here. I feel like we may have made a bit of an error, but I don't think it'll be that big of a deal. I think it'll work. It should work out, right? Even if it doesn't, we'll find a way. I'm just disliking the way that having this dt kind of looking thing, it's kind of... Yeah, here's what we'll do. We're not going to do this partial derivative. We're just going to go ahead and straight up say we're taking a variation of v of t, and then leave a dt there. And this is equal to 0. So one thing to keep in mind here, this is a very simple example. In many calculus of variation problems, you are going to likely have to use integration by parts. Maybe I'll do another lecture on that. I don't know, but look up like structural mechanics, calculus of variations, integration by parts. That's usually a pretty standard part of like the energy part of structures or something. Let me think about this here. Oh, did I forget the boundary conditions? All right, let's pause here for a second. I'm going to go back to the top on our model here. I just realized we forgot to set our boundary conditions, which are very important. So we have our point A and our point B, right? We need to define what our position needs to be at both of those points, right? So basically, here are our boundary conditions. X of t1 equals xa. Right, that's our first boundary condition, and x of big T, which is our is xt. All right, there we go. We got boundary conditions now. So another boundary condition we could do is say that velocity is just constant everywhere, but again, that would oversimplify it, and I wouldn't get to talk about what I wanted to talk about here. So, so now we need to do some thinking here. So we need to make this integral 0. And so the most obvious way to do something like that is say, well, okay, let's make this inside part 0, right? Because an integral of 0 is 0. So I think I'm just going to go ahead and do that. Although I have this feeling I'm missing something, maybe? Okay, I think it'll here it'll work out. It'll work out. We're gonna have to do a bit of a substitution. I probably should have just said. By the way, when you're doing these variation problems, I should probably point this out. Try not to think in terms of velocity, like position. Try to so we would start with position, and then instead of writing velocity, don't do that. Write like x dot or like dx dt, because it makes it a lot easier to keep track of, like, because you're thinking of derivatives of like the same kind of and actually when I give you the Euler-Lagrange equation and I show you how much easier this makes it, you're going to want to try to think of it that way. But yeah, essentially what I'm going to do here is I'm going to extract this, set it equal to 0, and instead of writing v of t, I'm going to write dx dt. Okay. And then maybe variation of v of t. I'm going to do a quick peek at what I did before here, because I feel like I might have made some kind of mistake that I'm not really thinking about. How did I end up with that? Okay, let's just let's just try to piece it together. This is a scuffed on the fly lecture right here. But yeah, this is not right. I'm gonna edit this out. It'd be nice if I had people watch these so they could just like tell me what I'm doing wrong. That's the thing about being a professor, like, I imagine, is just like you get your students constantly just fix all your mistakes for you. You forgot, Professor, you forgot a minus sign. You forgot a minus sign. What am I missing here? I've got to be... All right, let's try breaking it up, okay? Hopefully what I've said so far makes at least some sense. Anyway, we'll actually just be taking the variation of this entire chunky beast here. So the variation of 1/2 m. We're just gonna start using v squared, right? We can pull out these 1/2 m times the variation of v squared. Okay. I think I might see what I did wrong here. So this variation, we're going to take the partial derivative of this part with respect to time, I believe. Actually, I don't think that's what we're doing. What we're actually doing is we're taking the partial derivative with respect to v. That makes more sense. Yeah, so basically, in your integral, when you're doing these integrals and you're trying to figure out what to take the partial derivative of, take the derivatives with respect to the variables that you're trying to find and their derivatives. I can't believe that I blanked on that one, but anyway, all right. Anyway, with respect to v here, I mean, partial derivative with respect to v of v squared. And then we've got something like a variation of v on the end. There we go. That's what we're looking for. And now we can simplify this because obviously this cancels with that, and we end up with just a v. mv times the variation of velocity equals well, it would be 0. But now I'm getting to thinking again. Time. We're gonna do time, even though I said not to do that. Okay, here we go. 1/2 m times 2v times the derivative of velocity with respect to time times the variation of time equals 0. That, it looks like something that maybe we're looking for here. And then I think maybe hold on, let me check my older thing that I did here. Oh, I did end up doing it with respect to time. Okay. Oh, it looks like I actually made a mistake in the old notes, so but that's okay. Anyway, regardless, in order to set this, the variation of t can't be 0. Okay, we're basically going to go look through now and see kind of you know, what we can set equal to 0, what we can't. Right. Mass is just a constant. So is 1/2. We can get rid of that. We can get rid of 2 as well. Velocity. That's another quantity that we can't really just assume is going to be 0. So all we're really left with is change in velocity with respect to time. So our final differential equation for this system is basically just and we'll just go ahead and write it in kind of non, you know, precise notation and just say dv dt is equal to 0. Okay, that's our final thing. And then we can go ahead and pull up our boundary conditions that we had at first. So I'll just go ahead and copy those down here. It's probably going to copy some extra stuff, but it's not a big deal. Anyway, at this point, if we these are actually all that we need to kind of actually describe our system. But what I'll go ahead and do is we'll go ahead and derive the differential equations by integrating. So we basically have at this point v of t, and I'm assuming you know how to integrate something like this. That's kind of the audience I'm going for with this. V of t1 equals, we're just going to call it a constant. Okay, so then we need to integrate this, so we can instead of saying v, we can say dx dt, right, of t equals v of t1 plus a. All of the things on the right are constants, by the way. These are known value, or these are fixed constant values. So x of oh shoot, it's the furl. Hello. I got bored, so I decided I would do a lecture on something I've been messing around with, and I made a big mistake about like 5 minutes ago, and I couldn't figure out what I did wrong. Here, I paused the music I was listening to, so anyway, I'm just going to continue integrating this. What is going on? What is Cam doing back there? Oh, you're good. Anyway, I'm just going to go ahead and shoot, where the heck was I? X of t minus x of t1 equals, these are all constants, so we can say okay, v of t1 plus a times t, or actually that's not right, give me 1 second, t2 minus t1. All right, and so here is basically our final oh yeah, a is not acceleration, by the way. That's just a constant. Yeah, so we've got our velocity function. We've got our I guess we need to enforce our boundary conditions, right? So all right, well, we can go ahead and say x of t1 has to be x of a, or whatever. Basically, I'm just going to leave it at this. And by the way, at this point, I'm going to go ahead and talk about the thing that I said at the beginning that we weren't going to assume, and that's that velocity here is constant, right? So if we have any let's see here. Yeah, so if I were to like take the What did I do in my other note packet? I know I did something kind of. Yes, here's what I did. dxdt of t equals v of t minus v of t1 is a constant because I ended up with I see what I was doing here. Instead of dealing with this annoying dt, saying that dv dt is 0 is also saying that velocity is never going to change. So that basically confirms our intuition from the beginning that that velocity is going to be constant in the absence of any kind of energy field. It's just got a velocity and it's just going to keep going. And I guess from that I'll go ahead and do that. So just cross all this crap out. That's annoying and complicated. Just dv equals 0, v of t minus v of t1 equals, we'll call it a, and then let's see here, v of t, which is dx dt of t equals v of t1 plus a, and then x of t minus x of t1 equals kind of the same thing I had before, I guess. T minus t1 times plus a. Alrighty. There was something that I was gonna try to cancel out at some point, but yeah, it's oh yeah, okay, yeah. Basically, we know that this is the intuition that I was trying to get to. That's right. So basically, this v of t1 and v of a are just a constant, and as a matter of anyway, I don't know. There was supposed to be something at the end here about proving and finding acceleration or something. Yeah, I basically took the derivative of it, and then found that in a general case, the derivative of v with respect to time is basically we can say it's average acceleration. That was about all. But yeah, essentially we kind of got what we expected from which freaking notepad even was this freaking thing? I don't even remember. I think probably this one. Basically, all this basically says is that delta x equals delta t times times your velocity. And actually, if you substitute this in here, you end up with just v of t, right? Which is exactly what you would expect. So we derived our equation of motion using the principle of least action. As a summary, we started by defining variational calculus and the principle of least action. We defined our physical system as basically a mass particle traveling in one dimension with constant velocity. We defined our boundary conditions so that once we have our differential equation, we can actually find the equations of motion. We talked about conceptually what it means to take a variation and use that to find the minimum action. We compared it to normal calculus, where you just take the derivative and the second derivative to find the minimum. We define the Lagrangian as the kinetic energy minus the potential energy in a system. We set up our action integral and put in the energy, the Lagrangian of our system. Then we talked about how to take a variation and what the rules were for it, at which point we started taking the variation of the integral until we ended up with our differential, ended up with our solution, our equation of motion, with our boundary conditions, and combined them together to find an algebraic expression that relates the velocity of our particle, the time, basically the change in time, and the position of our particle. And the last thing I'm going to do is, I think I talked about this a little earlier. I'm going to talk about the, yeah.
So you're defining the you're trying to solve for kinematic equations, right?
That's right. Yeah, we're basically taking our physical system and finding equations of motion in the, this is basically the most general way that you can, and it works for any field. Principle of least action works in electronics, it works in aerospace, it works in mechanics, it works in geometry if you're trying to find like a minimum path or something. There's a lot of ways you can use the principle of least action. It's very general. It's just not necessary for like most people, because you usually just have equations or other laws that are easier to use. But it's just, I just think it's a, McNamara taught it. Did you take structures too?
Yeah, I mean, yeah, I took structures too, and we learned minimum potential energy and calculus of variation.
Yeah, so minimum potential, yeah.
It just seems like a really roundabout way of doing this, though. If you can assume there's no force field, right, or acceleration,
Yeah.
and
Well,
write it in constant velocity.
yeah, exactly. And that well that
Or that equation that's on the screen with dv/dt, which is just deltas because it's an average.
yeah, and that's kind of the thing though. I wanted to use a simple example to illustrate, because if I were to try to do like something that you would actually want to use variational calculus for, I would end up making a mistake and it would take me 5 hours to figure out why it's not working. So I spent like a half hour doing this, and then I went and like, I'm gonna make a lecture. Why not?
A cool way thing you can do with variational calculus is assuming that a line is the shortest distance.
Oh yeah, that's actually another really interesting example problem. I think the main difference between like this and structures is that in structures you're not integrating over time. You're integrating over usually like a distance, right?
Yeah.
Or an area or something like that, because the structure never changes in time. But having time kind of adds another layer to it where you can solve for dynamics. So if he ever ended up teaching like a structural dynamics class, he would probably end up talking about this. Um,
It would also be interesting to do it in a force field, so you don't have that acceleration.
yeah, so like you could have like a ball, right, and have a gravity field. Although except you wouldn't need, yeah, something like that, yeah. But yeah, basically the last thing I wanted to do was talk about the Euler-Lagrange equation, which I think Dr. Jemmy used a decent amount in when I...
Yeah, it structures too use that too.
Yeah, how do I spell this freaking thing? Euler equation. All right, so basically this is a very general equation that basically bypasses all the steps, annoying steps that you have to do when you do the calculus of variations. So just partial L, partial F. I'm just copying this from Wikipedia, by the way. Dx. What the fuck? Okay, so this is a spatial. For what we're doing, it would be dt. Partial L over partial F prime equals 0. So you just basically plug in your L and your functions, and you end up with your solution. So I can try to do it for this one, just as a quick kind of. So L equals 1/2 mv squared. And in this case, our F, we're going to replace it with X, and this will be X dot. And X dot is obviously velocity, so we can just go ahead and replace that. X dot. Okay. Partial derivative of L with respect to X. believe that is 0. And then we have negative d dt of partial L with respect to x dot. I believe this is in there. Let me use my math brain here to do this very, very complicated. Anyway, m x dot equals 0. Looks like conceptually what this is saying is that the velocity never changes with time, which is what we would expect. And what we can go ahead and do is we can go ahead and so basically we would have this dm x dot equals 0 dt, and if you integrate 0, you just get 0. So you could, but you could do that because but you already know that that's true. And I'm trying to show that we don't need to know that by using the principle that there's like no potential energy from that, we can derive that x dot is constant, basically. So just get rid of that, and mass can come out. This would be, wait a minute. Oh yeah, x dot, we'll just call it b or whatever, minus x dot of actually we'll just call it t1 equals 0. Cancel that out. This is a constant over on the right. All right, and we end up with x of t minus x of t1 equals, wait, did I forget to do something? I think I did, didn't I? I forgot the plus c. I forgot the plus c, Grant. I forgot the plus c. There we go. And then that's multiplied by t. And then we can add another constant plus b, except that this x dot of t1 is also a constant. So well, we've already shown that x dot is a constant, so we can basically just simplify this down now. So yeah, specifically though, x dot of well, we know x dot's constant, so then we just multiply that by t, and there we go. There's our equation of motion here. So I think that's about it. So basically we did the I guess just for fun I could do like the 2-line, like just assume velocity is constant approach, because actually I just realized that that's just Newton's first law. You just have to use Newton's first law and be like, the velocity won't change if there's no forces. So actually very, very kind that he came up with that. Well, yeah, but also, but if you just use that shortcut, you don't get to learn about the fun variational calculus. But now, like, what if you had like three, right, electrical particles, right? And then this was like a negative particle and a positive particle, and this was like a neutron, and like, and then there was, and then there's like a gravity field, except in this domain, the gravity field goes. That's where you like now need to start using because,
You start using numerical methods.
yeah, for real, true, true. Except for the fact that, well, actually, yeah, you could, but it's just the charged particles generate their own fields, and so you'd have to account for the fact that, yeah, and also
If you start getting a force field that's not constant,
at very small distances, I don't think that that even holds. I think you have to use the Maxwell equations, but whatever. This has gone on too long. I'm gonna stop streaming, stop recording, and I'll just enjoy the rest of the night.